One, right? Yeah. And Stachu is a prominent F# speaker and the host of the podcast, which has the best name ever, which is called WTF Sharp, which basically stands for what the F#, right? So I guess this is pretty much it. And Stachu, welcome to Minsk, and the stage is all yours. But you don't have a headset, right? You need to have it mounted. А кто может помочь нам замаунтить headset со звуком? Кто отвечает за звук? Привет. Okay, Sergey will help.
Oh, I gotta turn this on or something? Testing, testing.
Hello. Oh,
Good.
I think it works.
Yeah, that's
All right, cool. Cool. My name is Stachu Korick, and this is going to be solving Rubik's Cubes with F#. It's going to be a very different talk. That last talk was useful. This talk will not be useful, but it'll be fun. And we have Rubik's Cubes. I want to do things a little bit differently here. You guys didn't ask a single question during the talk last time, and I don't like that. I like little breaks once in a while. So I have bribes. So I have 5 Rubik's Cubes here. If you ask an interesting question halfway through, I will give you a free Rubik's Cube. So ask me questions. I understand that mic guys probably don't want to be running around a lot. Just ask the question. I will repeat it into here for the recording. All right, they'll be running then. Cool. So first off, thank you. Actually, first off, what's the inspiration for this talk? When I was a kid, I really enjoyed. This is really loud. Can I make it less loud? Is this good? All right, cool. When I was a kid, I really enjoyed playing with numbers. I did long division. I took the remainders of the number. I took the remainder, took the number there, and played with those patterns, trying to find patterns from that. I eventually moved on to another nerdy hobby, which is speed solving Rubik's Cubes. I spent probably 10 years of my life playing with these, going to competitions, talking to people that solve Rubik's Cubes. It was obsessive. I've been to maybe 30, hosted a few, been to nationals a few times. It was my entirely my life. My most recent kind of nerd focus has been F#, which is just a great language with a great community, and I get paid for it now, so which is great. So, but first, before I get and actually meet, I want to thank you for actually having me back. I was here a year ago. I wore a C# shirt to an F# talk, which got a little bit of trolling on Twitter. And I liked you guys so much that I ended up marrying one of you. Yeah. And I met her after giving an F# talk, so you know I'm not terrible, because she stuck around. Anyway, so thank you for having me back. I'm curious, how many of you were here last year? It was about August. All right, so a few. Cool. I didn't scare all of them away. So this is roughly the plan. We have this little intro bit here with some filler time. I'm going to give you an F# sales pitch. We saw a little bit of F# in Sergey's talk, but I'm going to kind of just sell it to you really quickly. I'm going to give you an on-ramp into domain knowledge regarding the Rubik's Cube. We're going to be using it a lot in the actual solvers, so you need to up-ramp you for a few minutes on how the cube works, how to think about it, and how to kind of break down the different concepts. After that, we're going to show a really inefficient solver. If you had literally an infinite amount of time, eventually the cube would be solved, but unless you're only a few moves deep, most of the time it would not solve correctly, or it would not solve in a reasonable amount of time. Then we're going to discuss efficient solver patterns. There's a lot of tricks you can do to basically improve the performance of a Rubik's Cube solver. So we're going to talk about what those tricks are and whatnot. And finally, I'm going to have a section for outro questions, including anything you're curious about related to F# or the Rubik's Cube. So first things first, I got to give you the sales pitch. F# is my favorite thing. As Ivan mentioned, I host pretty much the only F# podcast in the world. At this point, I married a person that I met through F#. I've been doing this F# stuff for a long time and actually get paid for it now, which is fantastic because it's still a pretty niche language. So what is F#? Well, it's been around for a while. It's pretty mature. It's been 1.0 officially released since about 2005, and it keeps on trucking along. Actually, 4.5 just recently came out maybe a month ago. I haven't updated this slide. It's open source since 1.0, totally free license, nothing restrictive there. is cross-platform since 2.0, so it's been able to run on Mac, Linux, Windows, etc. And it's functional first, which means it has a lot of functional kind of parts to it, like you can do monads and all that kind of stuff, but we're not going to worry about today. We're just going to talk about the language and talk about the fact that it can be accepting of OOP and imperative styles. So first off, FSharp is concise. In very few lines of code or very few characters, you can get a lot done. It's, a one-liner there, you have the numbers from 1 to 100. You do kind of a link syntax, and you pipe that, and you say, from those numbers, I want to take the sum, and from that sum, I then want to print it out. You can do that pretty quickly in one line. There's fewer curly braces and noise in the language. For example, within one line, you can have a little function there. It says square, x, and then returns the two x's. I didn't have to type any of the type signature or anything like that. The compiler figured out what the type should be, given the context of the usage later. If you want to call a function, very simple. Just call the function, no parentheses, nothing like that. Simple types are really simple. For example, if I wanted to domain model a person, all I would have to do is use something, what's called a record type here. We get these squiggles at the end here. You basically just say I have a first name, which is a string, a last name, which is a string, and that's my whole type. Down under the hood in IL, this will actually compile down to an equivalent C# class with 2 properties. So with very few characters, you can get a lot done. If you want to have more complex or more interesting types as your domain grows, you can do that, again, in very few lines of code. For example, we have an employee who is some kind of person, or is a manager, which is a person and has some subordinates there. And this is what's called a tuple, which basically means it has one of these and one of these. So within very few lines of code, you can do a lot of stuff. And it's great for showing this to business experts that you want to communicate. Does this actually make sense given the business requirements? FSharp is very convenient. So I know for a lot of the time, you want to have structural equality by default in your types. So if I actually have 2 John Smiths, if I try to do the equals for them, it shouldn't. I naturally don't want to have it check the object references. I want to check the internals and make sure that the internals are structurally equivalent. FSharp has that by default. If you do want that to be reverted and have reference equality, you can do that with just an attribute. So it's a lot of great convenient features. It is correct, so you can do less things wrong, which is always great. So a little bit fewer tests and a little bit more type checking for yourself. For example, here I have printfn, which is a function that takes in a string, which then inside of it, we can see with the %s, represents different types that it can take in as parameter, similar to string format. And this forces you to be correct and not try to pass in the wrong type or do anything like that. We also have units of measure. So let's say you're adding meters and feet, and you don't want to add meters and feet because it's going to blow up a space shuttle or something like that. You can fix that with type measures here. So I say I have a type m, a type foot, put an attribute around them, and it'll yell at you if you try to do bad math or math with different units. So it helps you out in not doing incorrect things. It's complete, so everything that C# and VBD can do, you can do in C#. So you can do classes, interfaces, abstract classes, all of your events, everything like that. There is a little bit of tooling that's kind of lagging behind still, but overall, it does pretty much everything that C# can do. And finally, I want to do a little quick FSharp demo just to kind of give you a feel for how I think in FSharp, because I think how you think is a lot more important than the little minor bits of syntax difference. So I'm going to put this down so I don't spill it here. So I have here, is this big enough? It's probably not big enough. OK, here I have some stock data. So in this case, it's basically just a CSV, comma separated values. Inside of a list here, that's what this structure is. And I put that inside of this list. And at the top, of course, we have some headers defining what all these are. So I'm going to show you what it kind of feels like to be developing in FSharp. So you have this task of I want to fill in this function. I want to get the date for the highest variance in stock. So basically, the question is, stock opens at a certain number, it closes at a certain number. You want to find what the highest variance is between those two numbers and return the date that associates with that. So as an F# developer, here's how I think about it. I see the problem. I define a function that relates to how I would kind of think of it. So for example, here I would say just get date for highest variance in stock, give me a string list, and return a string. And right now, obviously, this quote unquote test will fail. And I'm supposed to fill it in. My natural thing to do in F# is to first kind of pseudocode it out, write some fake code that will not compile, but will kind of give me a feel for how I want to solve it. So all I did, since that previous code in this code, was add some pipes here. They basically say, I have this data, and I'm going to use a link-like syntax, where I'm going to say, from this data, I want to skip the header row. I want to project to some kind of fancy type where I don't have just plain strings that I'm working with. I want to order by the difference between the open and close descending. So I'm getting the highest difference first. I want to take the first element, and finally, I want to get the date from the record. So just exactly how I mentally model the solution to the problem, that's going to be how I kind of pseudocode here. From this point, I can basically just fill in the code. All I have to do is solve the problem. It's just as simple as that. So I create some helper functions and whatnot, and very quickly I can come to solutions. So see here, I have that fancy type now defined. I'll just call it row with just the data points that I care about. I'll have some helper functions such as splitting some commas, parsing doubles, etc. And I'll just fill in these individual functions here. So that skip header row, I'll define it above and use it. The project to a fancy type, I'll define that above and use it, etc., etc. And very quickly you can get to a solved state. So something that's cool about F#, if you don't know, is if I highlight all of this and then hit Alt-Enter, the code will automatically be run inside of the little F# interactive window down here, which is nice. So here we can see that the result of this one is 313, which is what I should have expected if you go and look inside of the data. So very quickly, I can get from pseudocode, just kind of thinking about the idea, to an actual solution, which is really nice for me. All right, so that's enough of an F# sales pitch. Any questions before I get into the next stuff? OK. So a bit about the Rubik's Cube. So I've been to a lot of cubing competitions. It was pretty much my life. I averaged maybe 15 seconds to solve a cube. Two-handed, one-handed, it's a little bit faster. So before I go any deeper, I should probably prove that I'm not making all this up. Here, Sergey, you can scram me for a second. And to make it easier, actually, yeah. All right, good enough. All right, so I'm just going to solve this really briefly to prove that I'm not lying about all this. Again, I've been doing this for a long time. Unfortunately, I'm still not any good at it. The people that are good average maybe 8 seconds, which is a world of difference. But good enough. OK. So thank you. Talk over. As you can see, I've also solved it blindfolded and all that kind of stuff. So have a lot of cubing background at the end. If we have some time or in some kind of after-party situation, we can talk about all that. But for today, let's get to the actual background. If you are curious, I've hosted a number of competitions, and this is one video that I had someone make regarding the competition. This is actually something that my mother and I hosted for a charity event. So you can see a bunch of little kids running around and solving Rubik's Cubes. A really fun time. And some not so little kids. Anyway, there's me shaking someone's hand vigorously. So the physical structure of the cube, we're going to need to deal with this. We're going to need to represent this within code. So we should first figure out how this thing works. OK, so the Rubik's Cube, at its core, has a core. It's basically this little piece here that has 6 axes, or sorry, it has 3 axes, and different faces along each center. So we have typically 6 colors. White, yellow are opposite of each other. Green and blue are opposite of each other. And orange and red are opposite of each other. I'm actually colorblind, so I change my orange with red, my orange with black. I know what a bad hobby to pick, considering colorblindness, but oh well. Some interesting or some important notes to make here are that these faces can't turn relative to each other. So yellow will always be opposite of yellow, green are always opposite of green, etc. Finally, typically when you're writing a solver, you want to basically maintain the position. So I'm going to always assume that yellow is top, for example, and that blue is front, and everything else will work itself out relatively. And that's just for simplicity's sake. It costs extra code to deal with rotations, and we're lazy, so we'll get around that. So second off, we have edges, which are the pieces with two stickers on it, or two facelets, if you want to call them. Again, these will always have adjacent colors. So for example, I cannot have a edge that has a yellow and a white sticker, just because those are opposite faces. It's physically impossible. Very similarly, and sorry, there are 12 of those. Each one of those can be correctly flipped, or it can be incorrectly flipped. So let's say it's in its place right now. I'm going to grab something right here, a webcam, because I know you guys probably can't see too well. So what we have, that's the wrong camera. Actually, no. OK, so we have this cube here. I hope that doesn't give anyone vertigo. But anyway, so this cubey here is in the correct place, and it's flipped the correct way. It could also be in the correct place, but incorrectly flipped. Similarly, so there are 12 of these, and they can be correctly flipped or incorrectly flipped. Similarly, there are 8 corners. These cannot have opposite colors, so I cannot have a corner piece with both yellow and white, just because those are opposite. And also, these can be in one of 3 orientations. So it can be correctly twisted, which just means that this yellow piece is facing up. It can be clockwise twisted, or the other way, counterclockwise twisted. And we'll be representing these in our code in a bit. So as I mentioned before, we have corners as well. So there are 6 basic moves to the cube. I can do a right move, or an R move, which basically means that I turn the right face clockwise by 90 degrees. I can do an R prime move, which means I do the right face counterclockwise by 90 degrees, or I can do an R2 move, which means I turn it 180 degrees. And this is true for both right. I have to go a lot faster. I have to go both right, left, up, down, front, and back. Those are 6 different faces corresponding to those 6 different colors here. So an example algorithm looks like this. So algorithms are basically like notation you would have for sheet music. We have FRU, R prime, U prime, F prime. That does something in the cube, doesn't matter what for this talk, but it does something, and that's kind of how we write down how we're going to move the cube. I'm going to skip this actually, and let's get into creating a simple solver. Our goals here are to model the cube, show off some FSharp, and getting something on the paper. So first off, we can look at cubes in 3 different ways. We can either look at them at the sticker level, which turns out not to be too smart, which basically we'd have some kind of array that would represent all 54 stickers. We could represent it at the cubey level, which basically means I have an array of each individual edge and corner. Or we can do something where we kind of break down the things, and I have some int arrays that correspond to each of the orientations and permutations of the edges and the corners. We'll see that in a second. So first off, here's how we can represent the cube. We have edge positions, which is an int array. So if the edge is in its correct place, then it will go to that correct thing. So I've labeled each of these 0, 1, 2, 3, 4, 5, 6, 7, etc. I've labeled each position to be some number. And then when I'm turning the cube and I'm representing the state, the number that's in that position is corresponding to what piece is actually in that position right then. And I can manipulate that over around. A solved cube looks just like this. It's an array from 0 to 11, representing the positions in their correct state. Edge flips, nothing is flipped. 0 corresponds to that. Similarly for corner positions and corner twists. If I want to write some quick tests to deal with that, I can, just to verify that these are correct. Oh, there's a typo there. Oh well. So we have some stuff there. We want to be able to turn the cube. So what I've done is each one of these turns here manipulates those arrays in magical ways. And I have gone through basically painstaking efforts to go on paper and record how those arrays should be manipulated. And I can represent that in the exact same structure here. So we have this position here where I've dealt with all that. I have the most complicated bit of the whole solver here, where I actually execute that move. So in the first one here, I change the edge positions by taking a cube state, which is that 4-array thing. I have a transformation, which happens to be in that same exact data structure, and I apply those array mappings alongside that. And I can do the same thing with edge flips and corner positions and corner twists. So if you turn the cube, again, I've just done that here for R. I've hidden all of the other 6 basic moves. After I've defined the 6 basic moves, I need to define the other 12 basic moves, basically the inverts and the twice. So I can just do that here by saying D prime or D counterclockwise is D 3 times, just because if you take 3 rights, you get a left. So I have created basically a static class here that has a list of all the basic moves, which will be useful in a bit, so I don't have to reference them in line and array all the time. And if I want to, I can just verify here that executing a move leaves the cube in a unsolved state. We don't care about that test. I create a scrambler, which is nice and allows me to manipulate the cube, and so it's scrambled and such. Not very functional code, but it gets the job done. It's going to basically apply 25 random moves to the cube, or however many I say it to. I can verify that I actually scrambled. One important note, some math. Graphs are fun. So a graph is basically a bunch of nodes and a bunch of lines connecting them. The cube is a graph of about 43 quintillion nodes and a lot of arrows between them. So this is one state in the entire graph. And let's say I were to restrict the cube where I can only turn R2 moves and U2 moves. In this case, that's how big the graph is, just allowing those 2 kinds of moves. And for example, if I do a U2 from here, it'll get me back to there. If I do an R2 from there, it'll get me back to there, etc. The whole point is to keep in mind that all of the different possible states between, all the possible states in a cube can be represented in a graph. And this is useful because we can use depth-first searching to try to explore this graph. So from the given scrambled position, I want to go basically dive in and figure out how this is doing. So what I'm going to do here is I'm going to say, for however many moves you say I should solve up to, I'm going to explore this graph. So I'm going to start at this position. I'm going to send off some buddy of mine to go explore that tree, those branches of the tree, so I can basically turn the cube randomly in all those 18 ways, and then do that in all the other 18 ways as well. And I'm going to keep on doing that recursively until hopefully I find a solution. One problem with that is that it's a very depth-first search. So if I tell it go up to 10 moves deep, it won't have the, if there's a 5-move solution, it might accidentally find the 10-move solution first, which is not going to be good. So a way to deal with that is by using a breadth-first search, or an iteratively deepening algorithm. All that's really going to do is be a wrapper around that previous algorithm to increase the search depth for that function over and over and over until we find something. However, this is really slow. If you do something beyond 4 moves, everything's going to fail. There are 43 quintillion possibilities for the cube. Numbers get really big. Google can't do that. So if Google can't do it, you can't either, which is why we need advanced algorithms to solve the cube. And there's some trade-offs to consider here. I'll skip a few of them, but the important ones here for our sake are the move count, the resource requirements. Some solvers require a lot of CPU or a lot of disk space for pre-computation or a lot of RAM. And we care about the speed. How fast do we need a solution by? Can we wait a day, or do we want just a minute or a second? So we could port some human algorithms, but those lead to move counts in about 50 move count range, which isn't quite efficient for my taste. So what instead we're going to do is program the CoCMBA algorithm. So here's where the fun math comes in. It turns out that if you get the cube to a state where all the edges are oriented, flipped the right way, all the corners are oriented, basically twisted the right way, and you have all of the U layer edges and the D layer edges in the U and D layer correspondingly, then you can solve the rest of the cube using only this move sequence. So you don't need any R moves or L moves or single F moves or single B moves. And having this restriction allows you to search that tree a lot deeper, since 18 to the n is a lot smaller than, or sorry, is a lot bigger than, I don't know, 10 to the n, or whatever that number comes out to. So in order to program this sort of algorithm, so that could be what we do. We just basically apply that same IDA thing, and instead of checking for the solve state when we are doing the tree search, we have these basically a more loose equals, where you say, I think it's, it matches these requirements, but it's not exactly solved. So that's the way we could do it, but that's not enough. We need additional tricks. Number one, int arrays are pretty fat when it comes to a lot of positions, so we're going to store those cheaper. We're going to, and then we're going to do a lot of pre-computation, a lot of caching. So let's go through those different tricks here. So first off, you can store the cube state very, very cheaply. If I do an R move like this, it does some certain things. It manipulates those arrays in certain ways, and I can simplify all that data down very cheaply to just one integer. For example, I can take the fact that the URF, or the upright front corner, is counterclockwise twisted after an R move, and I can basically take that kind of data, basically take a ternary version of that, where I do this kind of math here, I get the result, and I can store the corner orientation in just one integer. Very similarly, I can store the corner permutation. I don't need to go into how all this math works, but point is, you can store it in an integer. So if we take advantage of that, if we take advantage of the fact that we can store everything very cheaply, that helps. But we run into a problem. Every time we want to then make a move and go from one of these crazy integers to another one of these crazy integers, we're going to have to decode from that crazy integer to the point where I can manipulate it using those arrays before that I kind of sketched out how the arrays are supposed to move. So what we have instead is we basically do all of the possible states ahead of time. So from every corner orientation possibility, which there are 3 to the 11th, from all those different things, we're going to pre-compute what each of the moves would end up in. So for example, I say, from the solve state, if I do an R move, how's the corner orientation going to change? I store that in a move table. So I store that in a table where it basically looks up what next integer should be applied. And that way, I get rid of that previous problem. Another thing I can do is reduce by symmetries. So this turn here in R is symmetrically identical to an L prime, just on the other side if you look at it that way. It turns out that there are 48 kinds of these symmetries, and if you take advantage of these symmetries, you can do lots of tricks where instead of having to go down 18 different roads whenever you're deepening in the tree, you can go down, let's say, 4 of them because you discovered some symmetries. So that's another way that this kind of gets improved. And the biggest thing is pruning tables. Pruning tables are the ability to store how many moves deeper, or how many moves deeper a algorithm would need to go, or a solution would need to go, in order to actually solve correctly. So I basically do a bunch of lookup to say I am, what's it called? I'm basically, okay, so basically store, go through all the possibilities of the corner orientation, the corner permutation, et cetera, like we did before, and you take each of those states by one of those integers, and we solve just for corner orientation, just for corner permutation, et cetera, and we store just the number of moves deep those would need to be, or need to go. And using those kind of lookup tables, I can basically say, if that pre-computed distance is larger than what I'm willing to do inside of the tree search, then just don't even bother going down that path. This happens to get rid of a lot of possible paths here, which makes our tree search much, much faster. They also take up a fair amount of data. So if you're doing this on some kind of IoT device, doesn't turn out to work too well. You can store more and more kinds of tables to make your cube solver faster. Let's say you wanted a cube solver as a service, CSAAS. You could do that with just basically gigabytes and gigabytes of data, and that would help you out a lot by basically doing a lot further pre-computation. You can also use suboptimal phase 1 solvers. So I mentioned there's 2 phases. First, it's going to solve up to that magical state where you can use that restricted move time. And you can also so you could do that. You could just go to phase 1, where you solve all of that, and then do phase 2, we solve the rest of the cube. But you could end up in a situation where phase 1 happened to take 17 moves, or not 17 moves, but 10 moves, and phase 2 took 10 as well. Well, there might be a phase 1 solution that was 12 moves, which led to a phase 2 one of only like 4 moves. Anyway, we're getting into complicated stuff there. So enough talk. You have a rough idea of how we actually solve it. So let's quickly see it in action. So if I go here and I and if I hit F5, we'll have a cube solved in 3 different ways. This code here, which I'll put online, actually has 3 different solvers built in. It has basically the beginner's algorithm that people use to solve cubes codified here. It has the CFOP method, which is basically the one that all of the professional cubers use. And when I professional, I mean salaried cube solvers. And it also has the CoCMBA algorithm. And you can see here it initializes some pruning tables and whatnot if need be. And there we go. We have the solution to the randomly scrambled cube. So lots of stuff, lots of math, lots of crazy. Point is we did it. If you want to see the code, I'll have it as soon as this video is online. I'll have it posted so you guys can go and see a bunch of FSharp code. But that's it. I really appreciate you guys having me here. I hope that wasn't too fast for you. If you have any questions, feel free to yell them out. I have some suggestions here. But thank you.
So thank you very much, Stachu. And the questions, and remember, the best questions get prizes.
Yes.
So.
Hello. Oh, Sergey.
All right.
He's close.
Do you know the maximum length of shortest path in this graph? 20?
20.
So in maximum, you need 20 moves to solve the cube.
Yep.
Any cube.
Yeah, any cube can be solved in at most 20 moves. That was actually proved in, I think, 2010 by a number of different people. If you go to cube20.org, you can see the history behind all of the mathematicians that looked this up. So as of 1981, we knew that 52 moves would suffice, et cetera. And as of 2010, it was actually released at US Nationals 2010 at MIT, which I was there. It was finally released that with actually a lot of Google servers, they basically rented Google servers. They proved mathematically that no cube can be, would take more than 20 moves. So 20. Most can be solved in like 16 though, but not by humans. Cool. All right, you get a cube.
We had a question over there.
Congratulations.
Do you agree with statement that difference between C# developer and F# developer is that the first one gets salary and the second doesn't?
The first one gets a...
Get salary?
Oh, get salary. F# is still pretty niche. It's a... I don't know. I get paid in it, so it works out for me.
In common.
It's not common. You're asking why?
Yes.
C# already big. It's hard for David to beat Goliath. It's there's a number of reasons that could be a whole other talk. But the short answer is that there's a big old Goliath named C# around there, and it's really hard for F# to come up and beat its head. You get a cube. Good enough. All right. Yes.
Yeah, I get a question about competitions. Like, how do cubes get randomized or scrambled for competitions? Like, is it the single position for all the competitors, or it's just a question of luck?
Yep. So I'm going to answer this question. It's going to take about a minute. So first thing is that I'll tell you the kind of competition organization, how it works. And that pretty much is each person that submits that they want to compete goes through a number of rounds of cubes. So I have 5 attempts per round. So let's say there's 100 people in the competition. Each of those 100 people will get pretty much the same exact 5 scrambles. So a computer will randomly generate a position on the cube, and then a cube solver will actually solve the cube, tell you the solution, and that solution is what the scramble people use, apply to the cube to scramble the cubes perfectly randomly. So that's how the cube gets done. You do that 5 different times. You take off your best and your worst time, and that's your average. If your average is good enough and it beats the other people's average, then you could advance to the next round, which the same thing happens over and over. That's the structure. Yep. And if you're curious about anything like that, go to worldcubeassociation.org. Yep. All right. Yes.
Yes, I have a question. I was wondering, is it possible to create algorithm that is going to solve cubes that has 3 sides or, for example, 8 sides, and it will be for all kind of cubes?
For all kind of puzzles? Yes. This solver will not do that. So there is something, if you go to speedsolving.com/wiki, this is basically, the #1 website for cubing. At least it has been in the past. If you go here and you go to puzzle solving, whatever, the short answer is yes. It's called KSolve, so you can look that up. It's a generic thing where you can, it generically solves different puzzles with moving pieces, and then you can input exactly how that specific group moves. So the Rubik's Cube, if you're into math at all, it's a group, which means certain mathematical properties applied to it. So you basically input how that specific group is manipulated, and from there it'll solve.
So it doesn't matter how many sides we have?
No, it does not. This solver will deal with that as long as you input the correct parameters. It may take a very, very long time, just because there's a lot of possibilities, and the cube might be very deep, or that puzzle might be very deep in terms of how many moves it can be scrambled. But the short answer is, as long as it's not too much, it's possible.
Thank you.
Yes. That's the last cube, I think, so sorry to the rest of you.
What if I break the cube? For example, I get unsolvable cube. I will change.
Who's talking right now? I'm sorry. Okay, cool.
I'm here. So what if I get unsolvable cube? For example, I change 2 corners in one diagonal.
Yeah, you can do things like that where if you have a twisted corner, so this cube is impossible. In fact, if you disassemble a cube and put it back together randomly, there's only a 1/12 chance that it's right, that it's going to actually be solvable. There's 1/3 chance that the corners will be twisted, a 1/2 chance that the edges will be orientable, just because you have to have an even number of edges misoriented. And the permutation, there's a 1 out of 2 chance that you'll have that right. So the cube cannot, there's no solver that can break time space. So you can't do that. Is that basically your question? Yeah. Or no? Cool.
Yes.
All right, any questions without a prize? Yeah.
Well, we got other prizes, right?
Yeah, the prize of having your question answered.
Hello. Is there a dependency between computer resources that we need to solve cube and cube size? For example, 5x5 cube. Is there like exponenta or any other function? If we have cube 5x5 cells on the round, we have cube with 5x5.
Oh, 5 by 5. You're talking about one of these guys?
Yeah.
Oh, cool.
Is there a function that describe dependency between computer resources that we need to solve problem?
Not necessarily. So there are. It depends which algorithm you use. So are you talking about for? Okay, let me rephrase the question to make sure I know it right. So is the question the following? Is there a correlation between the size of the cube and the computer resources required? Okay. The short answer is no, because you could supply a very simple algorithm to the cube. So I could just take the human algorithm that I would use to solve the cube for 5 by 5, which is a fairly simple method, believe it or not, and I could just do that. And any human algorithm applied to a computer, it's very easy to code, at least relatively, maybe a few hours. And then it doesn't take much time. It's going to take a lot of steps. So if you want optimal algorithm, then yes, the bigger the cube, the sadder you're going to be. Yeah.
All right, so we got time for one more question.
Sure.
Then we're going to be wrapping up.
All right.
All right.
Well, Alexey, thank you for the talk. I just wanted to ask, what's about Stack Overflow in FSharp?
What about what?
Stack Overflow.
What about Stack Overflow in FSharp?
Yeah, you know, functional languages, and probably they have some possibilities to manage recursive algorithms in a different way.
FSharp has some built-in things that avoid Stack Overflows a little bit more, but you have to deal with like, you have to do slightly special things. I can't go into too much because I don't have like that code in front of me, but you can avoid those situations for Stack Overflow.
Oh, you mean we need to form code in a special way to escape this situation?
Sergey, can you explain it? I'm trying to think like of how to.
Okay, no recursion, no Stack Overflow. Thank you.
All right, cool. What he said.
Yeah, we had a short discussion of tail recursion.
Yes.
All right, so we are wrapping up.
Sure.
We have 3 more special prizes. We have 2 T-shirts from our partner Playtika and 1 T-shirt of .NET by Community. So you have to pick 3 questions.
And 3 questions that were answered, or I have 2?
You have to pick 3 people who get the T-shirts.
Oh. Can I be biased?
Yeah, easily.
So 3 people, they answered questions. I'm going to pick Sergey. Oh, he got a prize. Well, I don't know. Oh, so he didn't get a prize, so I'd pick him.
Okay, 2 more.
All right. Who else didn't get a prize asked a question? That guy.
All right.
Was there a 3rd one? I don't know. Oh, yeah, him. That guy. Oh, he got a, yeah. Oh, well, he got a cube. I don't know.
Oh, all right. So we had 3 people picked. So thank you very much, Stachu. And we have a small present for you as well. This is a .NET by T-shirt. So you can wear it and advertise our community all over the world. So other people come and do the talks.
Thank you.
Thank you very much. So everybody, thank you very much for joining us today. We have a small networking session after all here. And then we're going to have an after party in Craftman Bar as usual. So I think Stachu will probably be joining us as well. So see you there. Like we will take off from here maybe in 20 minutes when we wrap it up here. So see you there maybe in half an hour. Craftman. Автопати в баре Craftman. Мы приедем там минут через 30. So then let's give a great round of applause for Stachu once again. Thank you, Stachu. And right now, the last but not the least, and probably one of